All right, so we're back to the charging example here, and I want to show something that's really interesting. This is related to our capacitor energy storage lecture that we looked at previously. And so, if you remember correctly, when I derived the capacitor energy storage equation, I looked at the multiplication or the product of the voltage across the capacitor with the current through the capacitor, and then I integrated that over time. And I showed that the integral over time of the voltage multiplied by the current actually gave me the energy stored in the capacitor. Okay, so in this circuit, I can do the exact same thing, and I can actually plot that product of the voltage and the current in LT Spice. We haven't looked at plotting a current yet in a transient simulation, but we're going to do that now. So let's go ahead and just run our charging circuit right back like we had in the one before our last video. If I go ahead and plot my voltage across my capacitor on one pane, I can go ahead and add another one. Plot the current in another pane. Maybe it's not clear why this is the case, why the current spikes up, so I'm going to reiterate what's happening. Initially, the voltage is 0 across my capacitor, and the voltage on my source is also 0, right? Let me throw my source voltage in right here so we can see it. When my source voltage rises up, right, you can see that my capacitor voltage is still 0. And so that voltage difference, I have 5 volts on my Vs and I have 0 volts on my capacitor, that gives rise to an immediate 5 milliamp current flowing through my 1K resistor, right? And we can even see, oh sorry, the way Spice is defining it is backwards. Let me go ahead and flip that. I'll rerun, nothing will change. So now I see my current flowing through R1, which is the exact same as my current flowing through the capacitor, right? As this voltage on the capacitor rises, my source voltage stays constant at 5 volts, so then that voltage drop, that difference in voltage across the resistor is getting smaller and smaller and smaller until it goes to 0. That's why my current is getting smaller and smaller and smaller until it goes to 0, okay? So that's just to explain why the current looks the way that it does. Let's now add another plot pane. And in this pane, I'm going to do something interesting. I'm going to plot my capacitor voltage, but then I'm going to right click or two finger click on it, and I can actually say I want to plot the capacitor voltage multiplied by the current through capacitor C1. And what does this give me? Well, this gives me a completely new waveform, which is the power. It's the power in my circuit, the power dissipation in my circuit. Voltage times current gives me power. Although there's no power dissipated by a capacitor. I haven't talked about that, but what voltage times current gives me is power. And if I take the integral of that, which I did previously in the lecture material, I can determine how much energy has been stored or has flowed into my capacitor and is now being stored in my capacitor. Okay, so if I want to take the integral of this, it's just the area under the curve, I can come up here and you can see in this window it says control left click to integrate. So if I hit control and then left click, I get this little window and it tells me the integral under the curve, the area under the curve, which is the integral, is 12.495 microjoules, okay? So if I were to go through and carry out 1/2 CV squared on this capacitor, I should see that the energy stored in the capacitor would be 12.495 microjoules, or very close to that value. Okay, so that is a really interesting application of using voltages and currents in LT Spice. It's nice that you can sit here and multiply by other traces. So I basically took, again, the product of the current through my capacitor, the voltage across my capacitor, and I get this waveform here. And I can take the integral or the area under the curve, and I can determine how much energy is stored in my capacitor, right? And that is 12.495 microjoules. So I'm going to go ahead and stop this video here. Just wanted to show that that was the case.